finishing up a homework 3 for me when? Somewhere soon, this weekend possibly. I'll be moving into homework 4 heavily today, and I believe I've already made it available to you guys, or no? No. Okay, well I'll get that up very shortly. Again, we're expecting the first midterm after homework 5, so probably most likely I'll give you the official 2-week heads up sometime next week for that. I expect we'll be on target for the week that it's labeled on the syllabus. Okay, any other admin or logistical questions before we get started? Okay, so here's what we were doing. We're trying to find a prescription if we have multiple individual forces acting on something. What will be the net force? So this requires us to learn about the process of general vector addition, and in this case, the vectors are forces. So let me remind you where we were at. Let's say we had 2 independent pushes and pulls on an object, and we wanted to resolve that into a net or overall force. Force 1 is 3 newtons in size, and it's 30 degrees from horizontal. F2 is 4 newtons in size, and it's 60 degrees from horizontal. And we can already make some very good predictions about where this answer should lie, so let's review those. First of all, if these 2 forces were not in these directions but directly helping each other, the most force you could get out here is 7 newtons. If they were exactly the same way, you get 7 newtons. So that's the upper limit we're looking at. Likewise, if they were exactly opposed to each other, 4 newtons one way, 3 newtons the other, that would lead to a 1 newton force. So we know that those are the very most extremes if we're talking about forces of this magnitude, but looking at any arbitrary direction they could have. We also looked at when they were perpendicular. So one was to the side, one was up, and we found that that had a force, net force of size 5 newtons. We could use Pythagorean theorem there because it happens to form a right triangle. And so I've got the minimum 1, the maximum 7, and then I've also indicated 5 here. 5, by the way, is not the midpoint between 1 and 7, but 5 is the net force when the 2 are perpendicular. And I'm expecting my result to come out somewhere between 5 and 7, because 5 newtons was when they were perpendicular, and these are more in the same direction. Okay, so they're generally more in the same direction than not. So I'm going to find out exactly what number that is. And then I also reason the angle. Well, if one force is at 30 and one is at 60, the exact midway point between 30 and 60 degrees is 45, but it's not going to be 45 because these 2 forces are not equal. One matters more. One has more force there. So we're expecting the result to skew towards the larger force, which is the one that happens to have the larger angle. So the answer is going to be somewhere between 45 and 60 degrees. Okay? So we have already narrowed down greatly what the answer should be. And of course, the point is when I show you how to do this in general, we'll land right on target, and hopefully you believe me that this process does work. So the process I suggested for doing this is exactly the same process you use with vector components. You put them head to tail. You connect the tail to first to the head to last. Well, the only difference being is that these aren't vector components, so there's no guarantee that they're perpendicular. And in this case, they aren't. So if I take one force, I put it head to tail with the other, and then I connect the tail of the first to the head of the last, there's my net force, but I have not formed a right triangle. This is a triangle which has really no symmetry of any kind. It's not a right triangle, it's not an equilateral or isosceles triangle, it's the most general triangle you can have. However, let me point out that it seems to be correct. We have 2 forces that are up and right, so it's no surprise that the net force is up and right. The length of it is going to be something a little shy of 7 newtons, because of course, if you added this length, 3 plus 4, that would be 7. But this kind of cuts the corner a little bit, so it's a little shorter than 7. So that seems about right. And the angle is also seeming like it's about right, because it's certainly bigger than 30. So this angle here is bigger than 30, but it's not as steep as 60. It's a little bit less than that. So seems to have all the right features. So let's take a look at how we might go about getting that. Now this is a triangle. Like I said, it has no symmetry of any kind. It's not a right triangle. It's not isosceles or anything. Nonetheless, you could probably pull out some obscure, well, not obscure, but some trigonometric stuff that we're not going to use, like law of sines or law of cosines, if you remember what those are, and you could probably do it. But even then, you'd just be getting lucky because we happen to have two forces that are added to form a net force, but you could just as easily have 7 different pushes and pulls, okay, or any number of them. What happens if you have 1, 2, 3, 4 different forces like that? Well, same process, you put them head to tail, and what do you have when you connect the tail of the first to the head of the last? Well, you don't have a triangle anymore. You have a generalized pentagon, okay? So obviously, at some point, there's got to be a better way to find out what is the length of that net force and what is its angle. So let me show you what that is. We can go ahead and leverage our idea of components. So I'm going to put in the components of everything. So I'm going to use my good old x and y axes. Haven't really strayed too much from this yet. And let me draw in the components of every one of these. So that's my F1x, my F1y. I'll do the same thing with the other individual force. Of course, here, by definition, the components are perpendicular. This will be my F2x and my F2y. I'm not only going to put in the components of the two individual forces, I'm also going to put in the components of the net force. So they look like this. So now I've got everything summarized along the coordinate axes. Okay, well, so what? Here's a move that I'm going to do. You may not want to, you don't have the ability to race as easily as I do, so you might want to do a separate sketch or just watch. Since I've got all the information about the vectors encoded in the components, I don't need to have the whole thing now. So I'm just going to, now that I have the components, I'm just going to look at those. And I get a kind of a nice boxy thing. Everything's obviously either horizontal or vertical now. And I noticed something. Look at the x components, this one and this one. So this plus this equals this. If you want to see it, I can draw it out separately. F1x and F2x form F net x. That's what's going on with the horizontal. And similarly with the vertical. If you didn't see it, here it is again. F1y plus F2y equals F net y. I can draw that out here. It looks like this. So I have just found an amazingly expeditious prescription for finding the net force as long as I'm willing to find the components first. Let me write down that prescription. If I want to find the x component of the net force, I add up the x components of the original forces. And this, by the way, works if you have 2 or 3 or 20 different forces. What you need to do is find their x components, add them all up in a row, and then add them. Once you add that, the net force is in the x direction is what you get. Same thing with the y direction. You just add up all your y components. This recipe is so easy to follow that we won't probably even bother from this point forward to draw the actual arrows head to tail. Okay? We won't bother to add the vectors head to tail and do a graph like this. If you like to, you can. But the main reason I did it was to prove to you that components is a way to do this as well and gives the same result. So really all you have to do is be proficient in taking your individual forces, breaking them up into components. X components go here, Y components go here. And then of course, once you have your net force X and Y components, then if you want, you can reassemble them into a magnitude and direction, size and direction. So you notice that these skills of breaking vectors up into components and reassembling is just a skill that you have to be completely fluid with. It has to be a part of your vocabulary when you're doing this stuff. Okay? So let's go ahead and do it for us. So I'll just go ahead and sketch my vectors like this. I have a 3 Newton force at 30 degrees. I draw in the components. Both of those components are plus. This is plus hypotenuse times cosine because it's the adjacent side. This is plus hypotenuse times sine because it's the opposite side. Okay, if you can't do it that fast, make sure you can by the first exam. There's no time for messing around with SOHCAHTOA on the exam. That's time wasted that you could be spending on something else. Okay, so let's go ahead and throw those in. 3 newtons cosine of 30 goes over here, plus 3 newtons sine of 30 goes over here. And then I, of course, etc. I need to do the same thing with the other force. The other force also has both positive components. It just switches out of 3 newtons with a 4 newtons and 60 degrees for 30 degrees. So I'll just go ahead and throw those in. So I've gone ahead and broken my individual forces into components. I happen to have only 2 forces, but if you had 17, the deal would be the same. You'd line up your 17x components on one line, 17y components on another. And then you just add these up. This comes out to be about 4.6. This comes out to be about 5. And then, of course, we can reassemble. How do we get the magnitude of the net force, or the size of it? This thing right here. Knowing both components. Also known as Pythagorean theorem, okay? You'll get 6.8 or so, right on the money, okay? Right, what we expected. Shouldn't be as big as 7 because they're not exactly in the same direction, but they're more or less very close to being in the same direction, so we get a fairly substantial net force. Okay, how do I, with the components, how do I get the angle? Inverse tan. You'll get, I think it's 47 degrees, give or take. Right on the money. Again, it's in the bin that we expect. It's somewhere in the realm of 45, 60 degrees. Okay, that is our prescription for vector addition. It's an incredibly, as long as you're comfortable breaking into components and reassembling them, the prescription is very easy. You just line up your x components on one line, your y components on the other, and then you go for it. We could even, of course, get the acceleration. That ultimately might be our goal. I think I told you that this mass was 2 kilograms. And so, of course, to get the acceleration, you just divide this by 2. So what is that? That's 3.4 meters per second square, and then same direction. Remember, the net force and acceleration are always in the same direction. Now, I should tell you something that will expedite things. So what we did was we had the net force in pieces, or components. We reassembled by Pythagorean theorem and inverse tangent. We use that to find the acceleration. But guess what? The very next thing we're probably going to do with them, and this is evidenced by like your projectile motion stuff, probably we'll split them apart into x and y axes again, right? So you might want to be concerned with the x and y direction separately. Just like your projectile motion problems, right? You're going to work a two-dimensional problem as two one-dimensional problems on parallel tracks. So let's skip the middleman. There's no reason to reassemble just to break apart again. So you can jump straight to here. And you can rely on the fact that the x and y axes are completely independent. So what you just realized is that the net force on the x direction is going to be the sole informer of any acceleration you have on that axis. And the net force in the y direction is going to cause the y acceleration, if any. Okay, so in practice, we'll just keep on two tracks. We will generally keep an x and a y track that are basically completely independent. They might share the time, but that's it. There's really very rarely any need to reassemble into a whole unless you're preparing a final answer. Okay? But in this case, what we would probably be doing, we'd be taking stock of individual forces that act on an object. We'd find out how much net force is in the x direction, how much is in the y direction, and then those would in turn inform how much acceleration we get on each axis, and we can of course tie those into the kinematics going on in the x direction and or the y direction. Okay? So we generally do this instead of reassembling just to take back apart. So that's how vector addition works. Are there any questions on that? Okay, so now you know how to take individual forces and assemble them into a net force. Net force, if any, leads to acceleration. Now we're just going to go ahead and start learning about forces in the real world. So various forces that might enter into a problem. Question? I'm not going to erase the entire board. What part do you need?
Just the content.
The more recent stuff?
Yeah.
Okay. So, forces in nature. We're just going to introduce a bunch of them. I think there will be a total of 4 for the first exam, and then that's a suitable cutoff point, and then we'll just introduce some more. The first of which, I'll tell you the first 2. I need at least 2 because I want to do some force addition stuff, and I need 2 forces to add. So the first one will be the force of gravity. The force of gravity has another name called weight. And of course, with any force, we need to learn about the rules of thumb for how big it is and what direction it points. So we'll write those down. And then my second force is going to be tension. That's the force from a rope or a string. And again, we'll come up with general rules of thumb for how big it is and what direction does it point, so we can take this knowledge to a problem and apply it. So those are the first 2. First notation. Force of gravity, I'll generally do F sub g. And again, if I want to refer to just the size of any vector, including a force, I drop the vector hat. You will see this commonly sometimes as weight. So be aware that that's a completely equivalent other notation, although I'll generally use F sub g. For tension, I'll use T vector. And if I want to refer to just the size, I'll say, of course, just T. All right? So let's start filling in the size and direction part. Well, the direction, that's easy. That's downward. So things get pulled down by gravity. Now that's the most generic way to say it. But of course, downward can be represented in many different ways. So for instance, if you choose upward to be plus y, then it's negative, right? Downward is negative. If you choose plus y to be upward, then downward is negative. If you choose downward to be the plus direction, then downward is positive. If you choose the plus y direction to be like this, diagonally, now you might think, why would we do that? Am I just messing with you? We will do that. Okay? Then which way is this? Is this plus or minus? It's neither, right? If you choose this to be plus, then this way is plus, and this way is minus, and this is some component business, right? So this can still be referred to as downward, but as far as actually doing some kind of thing to it, you'd actually need to break it into components, right? Along those axes. So you can see why I'm trying to refer to it as generically as possible. Downward is downward is downward. That's out in the real world. But plus, there's no, in the real world, plus, okay? Plus is in the eye of the beholder. It's what you choose to do. Okay. So let's talk about the size. Well, gravity, the one thing we actually know about it thus far, we've been using it already through homeworks 2 and 3, is that it somehow gives all objects the same acceleration, right? I am not going to give you any illumination as to why that is yet. All I'm going to do is make sure that that is in agreement with Newton's second law. So if F net equals ma, if A is the same for everything, then the force must be of size ma. So all I've done is said gravity is basically a force that gives everything this particular acceleration. There's no further illumination. In fact, this brings up more questions than it answers. And I'll get to that in just a second. But the one thing I do want to point out right now, and this is a common thing, okay, g is not negative. G is the size of the acceleration due to gravity. Okay, I can't emphasize this enough. Okay, g is not negative, okay? I don't know where this comes from, okay? Take a whole page in your notes, because I'll tell you, when you're doing your homework 4 or 5, there'll be at least 10 of you who email me and say, this is not working out, and it's because you're plugging in g is negative, okay? G is not negative. G is not the acceleration due to gravity. It is the size of the acceleration due to gravity, okay? And it purposely does not have the minus sign built in because you do not always want to choose downward to be negative. Sometimes you want to choose this, sometimes you do this, okay? If the minus sign was permanently stuck inside there, it would cause you a lot of trouble, so that is why it's not in there, okay? So this will come out positive, which it should because it's the size, okay? Okay, are there any questions on that? Okay. So let's see what this implies. This actually has a strange conclusion. Normally, if we had, say, a small mass and a big mass, if we applied the same amount of force to them, right? So we talked about this in the context of Newton's laws. If I applied the same force to them, would they accelerate the same? No. Which one would accelerate more? Small mass. It would look like this. more acceleration because that is less stubborn, and this, having more mass, more inertia, will not react as much to that external stimulus. That is not what gravity does. Gravity seems to be very strange because gravity will accelerate everything the same. So this is the same force, but for gravity, everything is given the same acceleration. So this is gravity. How can it give all things big and small the same acceleration? We are forced to conclude that it does not pull equally on everything. The force must be larger on which one? The big mass or the small mass? The big mass, that's right. Somehow gravity knows to pull on this one a little bit, but because this one has more mass,